Okay, so we'll continue. It's almost 6, but I think I will continue with the slides now, just for a few minutes left. So we will see in the later how the rearrangement occurs. Now, usually it comes with when you produce a carbocation, the one that it can stabilize the carbocation. So for example, you have the arrangement here of the carbon. You have CH3, CH, okay, and then a tertiary carbon here, CCC. But what you get in the product is you have your CCCC, okay, this one. So it's very, very different from what we started in the substrate, right? So, but you just have to look at it, get confused now. So we'll see later on the mechanism how the rearrangement occurs. So before that, before we go in details how this rearrangement, let's first talk on the mechanism of the dehydration of the alcohols. Okay, so let's focus for an E1 reaction. Our substrates are usually the secondary and the tertiary alcohols. So the first step in the E1 reaction is the protonation of our alcohol. So alcohol, our OH in our substrates, very difficult to leave, no? So what happens is that we protonate at first with our proton, and then we have our protonated alcohol. Okay, so once you have your protonated alcohol, then you get your, you can proceed to step 2. Okay, so step 2, see here you have your protonated alcohol, so the electron pairs of the alcohol will obstruct a proton from our acid, the H3O+. Now this is our acid. Of course, when you have your sulfuric acid, it dissociate with water to form your it's anion and it's proton, where it's the proton H is solvated with water. You get your H3O+. So your electron pair will obstruct this one to get your COOH here. So your alcohol now becomes protonated. So since you use the electrons to form a bond here, you get the double bond and plus. Okay. So once your alcohol is protonated, it's easy for alcohol to leave. You know, we have discussed that before, that OH is really very difficult to leave to form a carbocation. For it to leave, it has to be protonated first. So the water molecules can then depart. So it brings with it the electron pair, and then you get a carbocation. Once your carbocation is present, then our base will obstruct the proton adjacent to your carbocation. Okay, and then you will get your double bond plus your H3O+. So there are 3 steps in the E1 reaction mechanism. Yes, in the same way that we did the carbocation in dehydrohalogenation, we also obtain our carbocation in the E1 mechanism. In step 3, this one, no, when the base obstruct the proton, any of the 9 protons available of the 3 methyl groups, you have this, okay, 9 CM, 1, 2, 3, 3. It's possible to be obstructed. Any of the 9 protons available, the 3 methyl groups can be transferred to water molecules. And the electron pair left behind when a proton is removed becomes the second bond of the double bond. Okay, I already discussed that one. So any of those can be obstructed. So let's say you have your beta hydrogen here, any of those can be obstructed with water. Okay, you form your double bond. So once your base, water, obstruct this proton, you get a partial bond formation, and a partial bond breaking between carbon and hydrogen, and a partial bond formation between carbon-carbon, double bond, double bond, and then you get your double bond here, which is simply a sideways overlap of the p unhybridized orbital and the p unhybridized orbital of the carbon-carbon. So you get your double bond. The carbocation stability and the transition state proceeds with 3 degree. Of course, we've learned that the carbocation at 3 degree is much stable than a 2 degree carbocation than a 1 degree for a metal group. So the carbocation stability and the transition state. So you notice that for a 3 degree carbocation transition state, no, the free energy is actually much lower than a second degree than a first degree. And therefore it is much stable as compared to the other two. So again, for the tertiary alcohol, secondary and tertiary alcohol, so the E1 mechanism in summary, first is always the protonation of our alcohol. To get your protonated alcohol, so you have an oxygen with 3 bonds and a lone pair and a positive charge. Once you get the protonated alcohol, it's easy for the OH to leave, for the water to leave, and to form your carbocation. You remember your dehydrohalogenation reaction always form with your carbocation first, right? But in the dehydration reaction, there is a first step, which is the protonation before the formation of the carbocation. So pareha na siya, but there is just an additional step, no? Which is protonation. Step 1 is protonation. Why is that? It's hard for the living group like OH to leave your substrate, no, unlike your halogens. So it needs to be protonated because this one is a strong base, no, and it's very unstable when you get the OH. It's very reactive, so it has to be protonated. It has to become neutral when it leaves. No? Get your water here neutral. So once you have your protonated alcohol again, you can form your carbocation. So it's easy for the water to leave. It brings with it the lone pairs, the covalent bond to form your 2 dots here in oxygen and becomes neutral. Get your water. And of course, you get your positive carbocation. Once you get your positive carbon, then the base with the electron pair with it, you can use that one to abstract the proton. The proton, which is beta to that of the positive carbon. And the carbon-hydrogen bond will go to the carbon-carbon to form a double bond. And then you get your acid, your base acid pair. Okay, the reactions by which the carbocations are formed from protonated alcohols are all highly energenic. And it's based on the Hammond Leffler postulate, there should be a strong resemblance between the transition state and the carbocation. Where is our transition state? Okay, whenever you have this, so before you get your carbocation, no, there should be a strong resemblance in our transition state to that of our product for every step of the reaction. The transition state that leads to the tertiary carbocation is lowest in free energy. So we've learned this one here, the transition state for a tertiary transition state, no, for our tertiary, in the formation of our tertiary carbocation, the free energy is much, much lower than the 2 degree carbocation than the 1 degree carbocation. And in the Hammond-Leffler postulate, our transition state should be closer or resembles to our carbocation, like this one. So how you see our transition state, for example, you get three bonds here, and there should be a partial, you see here that there is a partial bond formation and a partial bond breaking here in the transition state to form your carbocation. And this is our transition state, and that transition state must resemble to this of the carbocation, closely resemble. And there are ways to stabilize our positive center here, developing positive center in our transition state. So since when the water, HOH, protonated alcohol, when it leaves, no, there is a developing partial positive charge on the carbon, there should be ways to stabilize the partial positive charge. And one way to stabilize that one is the hyperconjugation stabilization. So what is that hyperconjugation stabilization? It's the more alkyl groups, okay, is situated to your carbocation, the more you will have our hyperconjugation effect. It stabilizes, no? So the developing charge, positive charge, is stabilized, is most effectively delocalized in transition state, leading to tertiary carbocations because three alkyl groups are present to contribute the electron density by hyperconjugation. So what is the hyperconjugation? We have already discussed hyperconjugation before, no? So it is a sideways overlap of the sp3 hybrid orbitals and the p unhybridized orbital of this one. If you remember, you can review on what hyperconjugation is all about. So the more the alkyl groups are located or situated to your positive carbon or developing positive carbon, the more your transition state are stabilized, or the more your transition state are stabilized to lead to the formation of your carbon. Okay, so let's see before we end. There's only three. It's 9, 6, 10. Okay, so si Ronald and Ian. So Ian, rank the following alcohols in order of increasing acid catalyzed dehydration. So ABC, ano na lang, which one will be much more reactive for an acid, will be more reactive or more ease. There will be more ease of acid catalyzed, much easier rather, to undergo acid catalyzed dehydration. Is it A, B, C? Ian?
Confess gapan ko, ma'am, but I guess letter A.
Okay, so it has to do with the degree of the alcohol, you know. Let's see, the more the tertiary alcohol will be much more prone. It's much, if you remember the 1 degree alcohol, you have to require very harsh conditions. Secondary, much less harsher than the primary, the tertiary, much milder than the 3. So it always have to
Letter
go.
B.
Okay, you have to go with the tertiary alcohol. So the most easily the alcohol that would undergo more easily to undergo, how did I say, to undergo the dehydration is of course the tertiary alcohol, which is letter B, and the next is letter
C.
C, and the next is letter
A.
yes, so the last one is letter A. So next meeting we will do the mechanism for the E2, no? And then we'll discuss how do the rearrangement on the rearrangement of the alcohol, no, to yield a different product. We mentioned earlier there is a rearrangement. So we'll see that one in the next slide, next meeting. For now, that ends our discussion. And then where are the others?
Can I ask something, ma'am?
Yes.
In any mechanism nga atong na-discuss, why is it always the beta hydrogen atom ang na-involve, ma'am? And is there a possibilities na ma-involve ang alpha, ma'am? Ang alpha hydrogen atom.
Because it cannot be there's no way, no, because it's hard to abstract the alpha hydrogen. No, there's let's go back to dehydrohallucination. E1. Okay, so here, like for example, here you don't see a an alpha carbon here, right? So you get this is for an E1 mechanism, no? We don't see this one. We don't see an alpha carbon since this is a tertiary alkyl halide. No, we don't see an alpha. Let's see. We have for a primary alcohol. Like if you have a primary alcohol, you let's see if you have a primary alcohol. So this is a tertiary. Okay, let's say this for instance, this is your leaving group and you have your proton here. Ano yung kasabot? Like why we can't abstract this is your carbon, this is your alpha carbon. Why we can't abstract your proton? The reason is it's impossible to abstract the proton because it's hard to stabilize na the developing positive charge of the carbon. No, it cannot stabilize by itself if duha ang remember that we have already the leaving group that will leave this carbon. Okay. If if the hydrogen pagid is subtracted, it's not thermodynamically possible, no? Because there is no way to stabilize your duha if you have positive 2 na siya, no? Positive 2. It has to be abstracted. If it has to be abstracted, the leaving group, you have your leaving group already, no, biya siya. So there's a negative negative charge, negative electron pair here. So you have your electron pair diri. Okay, so any base that would abstract your proton close to an unshared electron diri because you already have, like say, imagine when the leaving group leaves, no, it brings with it its electron pair. Okay, it's an electron pair, and you have your proton here, hydrogen, and aromabulin, but so developing positive charge. Let's say an E1 mechanism. Okay, let's say you have here. In this case, you like proton because in the elimination reaction, the tertiary alkyl halides or alcohols are always favored in the E1 mechanism. So sometimes there is no alcohol, but in case, for example, there is sometimes there is no proton. Let's say that in case there is a proton, no, it's hard to approach the proton because it will furthermore destabilize your already developing partially positive carbon atom. Are you following, Ayan?
Yes, ma'am. Yes, ma'am.
So duha naman gud ang mawala siya ha. It's very difficult to stabilize already, you know. And the best way to stabilize that one is the formation of the double bond. Okay, when you have a developing partial positive charge and you have your carbocation, let's say butang na to, this is your hydrogen, dili ni sa H3, no? How are we going to stabilize the developing positive charge, which is the proton here? No, so nanakay living group, niya na imong living group here. For example, let's say dili ni siya sa H3, this is a hydrogen, and this is your alpha carbon. Okay, pag nibiya na si chlorine, for example, your living group, you have this, and this is your proton, for example, H+. That will be your alpha hydrogen because it's contained on carbon. In your chlorine, your living group. So imagine if you have your proton here, and saan mo pag-stabilize kang proton? So dili siya pwedeng ma-remove si proton because it will furthermore destabilize your carbocation. The best way to stabilize your carbocation to disperse the developing positive charge is the formation of a double bond. No, so formation of the double bond to stabilize this one. So you get your molecule here. Are you following, Ian?
Yes, ma'am. I think I get it.
So we always that's why any group of atoms that could stabilize the developing positive charge of the carbocation of the when the leaving group leaves, in the case of E2, any way to stabilize the positive carbocation would lead to the formation of your transition state and eventually your product. And that is why one reason that whenever you have more alkyl groups, like CH3, it will always stabilize the carbocation or the developing positive charge by virtue of what we call as the hyperconjugation or by virtue of the electron withdrawing inductive effect. So by electron withdrawing electron donating inductive effect. So these alkyl groups are always contain electron density with it, so it can just induce, like share, flip its electron charge to disperse the developing positive here. Secondly, or primarily, you have the hyperconjugation. You have your CH3 here, where it uses the sp3 hybrid orbital. So you have sp3, 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 bonded by sigma bond bonded to hydrogen. So there is an sp3s bond with hydrogen. So each of the carbon hydrogen is formed by a bond sp3 of carbon and S hydrogen. Okay, so you have an sp3 orbital here is a carbon. And if you remember, your sp3 hybrid orbital is 25 p character, no? And by virtue of sideways overlap, overlap niya sideways, sideways overlap, i-share niya yung sp3 electron density. Okay, stabilize niya ang positive charge here by virtue of the hyperconjugation. If you remember your pi-pi orbital, it's formed by sideways overlap. Diba na kay p unhybridized orbital and p unhybridized orbital. Let's see here. Kani? Okay. You have an unhybridized p orbital here, and the other one, if you have, this one is an sp3. If you have another unhybridized p orbital here, that's this one, p unhybridized orbital. It uses the sp2. Remember that when you form a double bond, it utilizes the sp2 hybrid orbitals, 3 bonds, and 1 unhybridized p. So if the p unhybridized contains an electrons, then it do sideways overlap to form the pi bond, right? So it's a sideways overlap to form your pi bond. And the sigma bond is a head-on overlap. Kanang head-on, kanang head-on. It's not sideways, no? Kanang front kibali. So sp3 for instance, but this one sp3 sp2 for this one sigma bond. This is a sigma bond. This is an sp2s sigma overlap, no head-on overlap. sp2s sigma overlap. sp2 and sp2 carbon, this is where your sigma bond is. So the carbon-carbon bond is made up of an sp2 and sp2 orbital head-on overlap. Pi bond is made up of pi sideways overlap. Mura siya nag-flip sideways, no? So up and below the plane, you have your pi. This is where the electrons can mostly be found, no? Up and below the plane. That is your pi bond. In the hyperconjugation, you have your sp3 here and you have your p here, unhybridized and no electron pairs. So siya klaro diri ano. So mura na siya, dili siya mostly parallel, but close to parallel in an sp3 direction. So the sp3 geometry. In the sp3 geometry, you remember it is in a tetrahedral manner. Okay, so I think I have already shown that one before, and it can be stabilized by hyperconjugation. See if I have this name. So the more, I'll show that next meeting. The more R groups, actually that is contained, that is in the adjacent carbon atoms, the more it can be stabilized. No? So here you have your alpha carbon and you have your R group here, carbon here. So it's easy to stabilize this by virtue of the hyperconjugation. So that's why for the stability, the 3-degree alkyl halides or 3-degree alcohol will always have much easier way of producing our alkenes, because of hyperconjugation. And we will discuss that later,
Thank you, ma'am.
Okay, so wala na anyway, so I will emphasize that. I think I have mentioned this one. The hyperconjugation stabilization is greatest for tertiary carbocation. Okay, so If you want to review on the hyperconjugation, you can go back to I think chapter 6 or yeah, chapter 6 ba to nga we discussed of hyperconjugation. I think also I will look at what chapter that I discussed in hyperconjugation. Okay. That's all for today, and we'll continue with dehydration reaction next meeting. And we have so far discussed on the E2 ba? Or E1. E1 di I know because we form a carbocation. So next meeting we talk about the E2 for a dehydration reaction and then some examples. So that ends our meeting for today. I hope that you've learned something. And yeah, just feel free to ask. And also for your problems, now you have your problems, if you have some questions, you can also ask me. So that's all for today, and see you next meeting. For your attendance, please indicate in the LMS. So we're over time already. And, yes, also for you to practice more, always do the exercise problem. Para maanad mo. Okay, so bye everyone and see you next meeting.
Bye, ma'am.